We will continue to solve the 1D wave equation, which is given here. So this 1D wave equation is a hyperbolic PD equation. We are using the similar strategy to solve this problem, similar to the previous heat equation. In this problem, we are going to find the vibration, which is given in the U symbol, with respect to x location as well as the time. By using the separation of variable method, the solution will be equal to the multiplication of the function between the x and the t. This can be simplified into capital XT. So you have differentiate u with respect to t twice, therefore this term is equal to xt double prime. Differentiate u with respect to x twice, then you obtain the x double prime t. Then you should obtain xt double prime equal to c square x double prime t. Let's move the x to the right hand side and the c square t to the left hand side. With that, you success to obtain your t function on your left hand side and the x function on your right side. So this is known as the separation of variable. So this will be equal to negative lambda in order to obtain two ODE equations. And then you need to consider three cases where your lambda equal to 0, lambda equal to negative, lambda equal to positive. So your alpha here must be greater than 0. From the given initial and boundary condition for this PDE, you can find the eigenvalue and eigenfunction for each case here. Once you find the solution for the first case, second case, and third case, you need to apply the superposition principle to find the total solution by taking the summation of all of the solutions. If the total solution has unknown coefficient, then you may need to apply the half-range Fourier cosine or sine series expansion or the full-range Fourier series expansion in order to find the unknown coefficient. In fact, we are using the same strategy to solve the wave equation here, similar to the heat equation that you solved previously. Please make sure you master this strategy. It's very important. In this example, you have a guitar and you want to study the vibration of the string here from this guitar. So you can see the string is fixed at both ends here. Let the direction here to be x, then you obtain x equal to 0 to indicate this point, x equal to the total length to be this point. Let the vibration in the vertical axis here to be u. So u is your vibration in this direction. Therefore you can see at these 2 points, the vibration will be equal to 0 for all the time. So for this point, the x is equal to L, therefore you can write ULT equal to 0. And here you have x equal to 0, therefore the vibration at x equal to 0 for all the time will be equal to 0. These are the boundary conditions for this guitar string. So you should obtain this boundary condition for the guitar string here. Imagine that you pull the guitar string upward. So you are actually apply the initial displacement to the guitar string. Therefore, for the initial condition, you have at t equal to 0, you apply the vibration at x location here to be a fx function. So fx function is actually the initial shape that you apply to this guitar string. So this is the initial displacement that you apply to the guitar string before you release it. If you pull the guitar string and hold here to make this thing at rest, then the initial velocity will be equal to 0. This is because before you release the string is at the rest position, which means the velocity equal to 0. On the other hand, if you pull the guitar string and release it immediately, then this will not in rest position, but it consists of some initial velocity at all the x location here. Therefore, in this case, your gx will not equal to 0 and your initial velocity will be equal to some function gx. In this example, we have the wave equation given in this format. and you can use the b squared minus 4ac to identify the type of PDE. Since the value is greater than 0, therefore is a hyperbolic PDE. In the first step, we use the separation of variable method. So you can see that from here, your dependent variable is u, independent variable is x and t. Therefore, using the separation of variable method, your solution must be the multiplication of the function for the independent variable, which is equal to x function multiplied with t function. So you need to differentiate u twice with respect to x. So this is the x double prime t. Differentiate u with respect to t, you obtain xt double prime. You need to rearrange this equation into this format. Then let this equal to negative lambda. When you compare the second component here to the third component, you obtain the first ODE equation. When you compare the first component and the third component here, you obtain the second ODE. So you have success to obtain two ODE from the PDE here. For the first case, we assume the lambda equal to 0. So we substitute 0 inside the lambda here, you obtain these two ODE. You can use the characteristic equation approach here to solve these two ODE because they are both homogeneous ODE. So you can convert the t double prime into r square equal to 0. Therefore you have repeated root equal to 0 here. Substitute the 0 inside the solution here, you obtain the exponential 0t for both solutions. To avoid linearly dependent solution, you need to multiply t in order to obtain independent solution. So you can combine the solution 1 and solution 2 by using the superposition. And don't forget to multiply the constant c1, c2 to your solution. So exponential 0t here give you 1, therefore you obtain the first solution for t equal to this answer. Similarly, you obtain repeated root in this case, which is equal to 0. Substitute inside the solution here, you obtain exponential 0x for both of the solutions. Therefore, you need to do the treatment and multiply the independent variable x here. Lastly, you can take the superposition and multiply the constant c3 and c4 to these two solutions, and you can obtain the total solution for x function. Exponential 0 gives you 1, therefore you can simplify it into this. Then you need to multiply the x function and t function here in order to obtain the PDE solution for first case. For the second case, we assume the lambda equal to negative alpha square, where the alpha is greater than 0. Substitute the lambda equal to negative alpha square here, then you should obtain these two ODE. Let's solve the first ODE, so you can convert the t double prime into r square, negative alpha square a square t into negative alpha square a square. This is your characteristic equation, and you can rearrange to obtain the r equal to this. Square root of the alpha square a square give you plus minus alpha a. Therefore, you can substitute this r inside the exponential answer here. Then you can obtain the first solution in the exponential alpha at and second solution in the exponential negative alpha at. Then you take the superposition between the first solution and second solution, and don't forget to multiply it with the constant. You should have learned earlier that the exponential format here can be converted to the hyperbolic cos and hyperbolic sine format. So remember, when you have the root equal to a plus minus real number, then we can directly convert into this format. This is much more useful in the PDE, so we do not use the exponential format here. Let's continue to solve the second ODE here. X double prime can be converted to r squared, negative alpha square x can be converted to negative alpha square. Rearrange this equation, you obtain your root equal to plus minus alpha. Since this is real number, therefore it can be converted to hyperbolic cos and hyperbolic sine format. Multiply the x and t solution here, then you obtain the PDE solution for second case. In the third case, the lambda equal to positive alpha square, where the alpha is greater than 0. Substitute the lambda here equal to positive alpha square, then you should obtain these two ODE. And we need to solve this. Let's start with the first ODE. So you can convert it to the characteristic equation here by convert the t double prime into r squared, alpha square a squared t into alpha square a squared. So from here you can rearrange to obtain the r, and your r is in plus minus imaginary number. So we know that plus minus imaginary number can be converted to the cos and sine format for the t solution here. We can use the same approach to solve this ODE. First of all, you need to convert to the characteristic equation by convert the x double prime to r squared, alpha square x to the alpha square. From here you can find the root, and your root is equal to plus minus imaginary number. Therefore you obtain the x solution in the cos and sine format. So you need to multiply the xt here in order to obtain the PD solution for third case. So this is the answer. So far you have considered three cases, and after you solve the two ODE for each case, you success to obtain the x and t function, and multiplication of it, you obtain the PD solution. So you repeat the same procedure for the second case and third case. So these are the PD solution that you obtain so far. Let's apply the condition to find the eigenvalue and eigenfunction. For the first case, you obtain the PD solution equal to the t function multiplied with the x function here. Let's apply the first boundary condition here. When the x equal to 0, your vibration u equal to 0. So you can substitute x equal to 0 inside here. You obtain C3 on the right hand side. And the C1 plus C2t, which is the t function, will be remain. And the u will be equal to 0. We know that the variation u here is dependent and change with respect to time. Therefore, the t function here cannot be equal to 0. So this function cannot be equal to 0. Then your C3 must be equal to 0. In mathematical point of view, you can imagine that C1 plus C2t here is a linear function. And since your t is greater than 0, so it will be in this region. And you can see this function will be never equal to 0. Since you obtain the C3 equal to 0 here, you can substitute inside the original PDE, then you success to obtain the new PDE. We continue to apply the second boundary condition. Substitute the x equal to L here, you obtain u equal to 0. So x here will be changed to L, then in this case your u will be equal to 0. So you success to obtain this equation, and since we know C1 plus C2t here is not equal to 0, therefore C4L here must be equal to 0. And when you look at this term, L is the length, L cannot be equal to 0, therefore your C4 will be equal to 0. Since you obtain C3 and C4 equal to 0, therefore this component will be equal to 0. Multiply it, you obtain the PDE solution to be 0 in this case. And there is no solution for case 1. For the second case, this is the PDE solution, which is equal to the t function here multiplied with the x function here. Let's apply the first boundary condition. Substitute the x equal to 0 inside. You obtain this term equal to 0. Hyperbolic sine, you obtain 0. Hyperbolic cos 0 gives you 1. Therefore, you obtain C7 only, and your u will be equal to 0. So when you compare this, you know that the t function cannot be equal to 0 because the variation here is depend on it and is changed with respect to time. Therefore, the time element here must be as is. So since this is not equal to 0, therefore your C7 must be equal to 0. So you can substitute the C7 equal to 0 inside the PDE equation here, then this component can be eliminated, and we continue to apply the second boundary condition. By substitute the x equal to L, you obtain the u equal to 0. So you substitute the x here equal to L, then your u will be equal to 0. Therefore you should obtain this equation. And you can see that since this t function here cannot be equal to 0, then this component must be equal to 0. We know that the hyperbolic sine here cannot be equal to 0. because the hyperbolic sign will be equal to 0. In fact, you should know that the hyperbolic sign here can be equal to 0 when the alpha L is equal to 0. But since the total length here is not equal to 0, and the alpha here is greater than 0 and is not equal to 0 as well, therefore the alpha L is not equal to 0. So you should obtain the hyperbolic sign alpha L here not equal to 0. Since the hyperbolic sign term here is not equal to 0, therefore you obtain your C8 equal to 0. So you can substitute the C8 and C7 inside the PDE here. So this term can be cancelled. So 0 multiply the t function, you also obtain the 0. Therefore you obtain the U2 equal to 0. That means there is no solution for case 2. This is the PDE solution for the third case. Let's apply the first boundary condition. So you have x equal to 0, then your u will be equal to 0. Substitute the x here equal to 0. Sin 0 gives you 0, cos 0 gives you 1. Therefore you only have C11 here. And the u will be equal to 0 when you substitute x equal to 0 here. Since we know that the t function here will not be equal to 0, because the u vibration is dependent on the t function. Therefore, the C11 here must be equal to 0. With that, it's success to obtain this information. Substitute this information inside the original PDE here. Then you obtain the new PDE to be this. You continue to apply the second boundary condition, where your x is equal to L to make the u equal to 0. So substitute the x equal to L inside to make the u equal to 0. So you should obtain this equation, and you know that the t function here cannot be equal to 0. Therefore, your C12 sin alpha L here must be equal to 0. Since we know that the sin alpha L here can be equal to 0 when the alpha L is equal to n pi. Therefore, the C12 will not be equal to 0 in this case, and you have the solution for U3. You need to be careful to select the integer n here. It must be positive number. Although the sin n pi is equal to 0, for the n can be any number from negative to positive value. However, due to the alpha L here will be always positive because you have the alpha greater than 0 and your L here is greater than 0 as well. Therefore, the n pi here must be a positive value as well. So we cannot have the negative value and we cannot have 0. It must be start from 1 and above to obtain the positive value. So your n must be start from 1 and so on. Since you know that the alpha L will be equal to n pi, rearrange this equation, you obtain your alpha equal to n pi over L. So you substitute this information inside the alpha here. Then this is the solution for U3. Since you have n solutions here from n equal to 1, 2, 3 and so on, therefore this is no longer a single solution. It will be a multiple solution with n index. This is the PDE solution that you obtain for these three cases, and you have no solution for the first case, therefore we cannot find the eigenvalue and eigenfunction here. You obtain multiple PDE solutions for the n index from 1 to 3 and so on. So this is the answer that you obtained previously, and you can further simplify it by multiply the constant here inside to give you a new constant A3n, and if you multiply the constant inside here, you obtain a new constant B3n. In this case, your alpha is equal to n pi over L. Substitute inside this equation, you obtain n pi over L squared. Therefore, this is your eigenvalue. So you should obtain the eigenvalue equal to n pi over L squared here. Since you have multiple eigenvalue with n index here, therefore you change the lambda into lambda n. Eigenfunction of the PDE is just the solution to this PDE. Therefore, the PDE solution that you obtained previously is the eigenfunction. This is just an example. When you substitute the n equal to 2, you obtain the eigenvalue at mode 2 and the corresponding eigenfunction at mode 2. So far, you obtain multiple solutions from case 1 to case 3. So you need to perform the superposition principle to find the total solution. So you substitute the solution for the first case, solution for the second case, solution for the third case for n equal to 1, solution for the third case for n equal to 2, and so on. So you will obtain the summation of this solution from n equal to 1 to infinity. And you can multiply the sine term inside and expand it to obtain the sine cos component and sine component. This is the total PDE solution after you apply the superposition principle. So you have to apply the initial condition in order to find the unknown coefficient here. Since you have two unknown coefficients, therefore you need two initial conditions to solve it. For the first boundary condition, you have the t equal to 0 to make the u equal to fx. Therefore, you substitute the t equal to 0 inside, and sine 0 gives you 0, so this component can be cancelled. Cos 0 gives you 1, and this term will be equal to fx. With that, you success to obtain the fx function equal to the summation of the sine term, and you should recognize this to be a half-range Fourier sine series expansion, where the x is from 0 to L. And you should know that L is your tau. And for the half-range expansion, half period, which is the P over 2 or L, will be equal to tau. So these are two different definitions. This is length. This is half period. So in this case, they are equal. You can obtain the omega directly from here by knowing the general formula is n omega x. Therefore, the omega, when you compare it, you obtain the omega equal to pi over L. You can also obtain the omega from here, where you know omega equal to 2 pi divided by period, and 1 period is equal to 2L. Therefore, from here you obtain pi over L also. So you can substitute the half range here equal to the total length, the tau here equal to the total length, and omega equal to pi divided by total length. Normally the total length will be provided. So let's say in this case it's given 5, and the fx function, which is the initial condition, will be provided as well. Let's say this is in the x square function. So from these two information, you can substitute all the L here to be 5. And your fx function here will be equal to x squared. So after you solve this, you should obtain your coefficient for A3n. Previously, you have success to find the A coefficient here. Next, we are going to find the second coefficient. So to find this coefficient, we need to apply the second initial condition here, which need to differentiate the u with respect to t. Therefore, you need to differentiate the u here with respect to t. To do this, the x function here will be remain during the differentiation. The constant a and b here can be remain as well. Then you need to differentiate the cos, give you negative sine, and you need to multiply with the coefficient inside here. Differentiate the sine here, give you cos, and you need to multiply with the coefficient inside here. So this is the result after you differentiate it with respect to t. Let's apply the second initial condition here. So you need to substitute the t equal to 0 inside the du over dt here. Then you obtain the gx answer. So after we substitute the t equal to 0 here, then sine 0, this component will be eliminated. You only have cos 0, which gives you 1. And you have the b multiplied with this coefficient and the sine term, which is over here. And this result will be equal to the gx function. So you success to obtain the gx function in the summation of sine term, and you should recognize this is a half-range Fourier sine series expansion. Therefore, we can obtain the coefficient inside here, and you need to be careful. The coefficient for the half-range Fourier sine series expansion is all of these components. These are the coefficients. Therefore, you put this coefficient on the left hand side, and this is equal to the formula here. So previously we successfully obtained the tau equal to L and the omega equal to pi over L. So you can substitute inside omega to be the pi over L and the tau to be L here. And you can see that this component can be cancelled, and you shift this to the right hand side, you obtain this answer. So after you solve this, you should obtain the B coefficient. Normally the L and Gx will be provided. So Gx means the function in x variable. So you have, let's say, something like this, x. So the length, let's say, is 5. Then you can substitute the Gx equal to x here, and your L here to be 5. Now you can solve this problem. With that, you success to obtain the coefficient A and B here by using the half-range Fourier sine series expansion to be this answer. After you substitute the coefficient inside, then you success to change the general PD solution into particular PD solution. So these are the PD solution that we are looking for. So far, you have success to solve the wave equation and obtain the particular PD solution. So U is the vibration at the vertical direction, X is the position for the string. And you know that at t equal to 0, the string is fixed at these two sides, and this is the initial condition, which is given by Fx. And the initial velocity for this string at this moment is given by Gx. If you want to know the vibration at x equal to 1 here, then we can substitute x equal to 1 inside this formula. If you want to know the change of the vibration u over the time from t equal to 0, 0.2, 0.7 and so on, then you need to substitute the corresponding time. For example, let's say you want to know at x equal to 1, what is the vibration at t equal to 0.2. Then you need to substitute 0.2 inside. And after you solve this equation, you obtain this answer, around 0.5. You can continue to substitute t equal to 0.7 inside here after you compute this series, and you obtain at x equal to 1, the vibration is around negative 0.3 here. You can continue to substitute various time here into this equation, and you should get the corresponding vibration here at point x equal to 1. By repeating the same procedure at all the x locations here, then you should obtain the blue color result in all the time. So now you can see the change of the vibration shape from one moment to another, and it keeps changing and reducing over the time. In this study, you should focus to solve the PD equation like the wave equation here in order to obtain the corresponding particular solution. So this is your main focus.